Hello everyone, welcome to my talk in OFDM-based visible light communication with probabilistic shaping. My name is Tilahun Zerihun Gutema. I am a PhD student at the University of Edinburgh, supervised by Dr. Wasiu Popoola. I want to start my presentation with a simple question. Imagine you have a cylindrical pipeline to transfer a cube or a cylindrical material. Which of the materials would you choose to get the maximum flow through the pipe? I'm sure you'd agree with me that it's the cylindrical material which will utilize most of the cross-section of the pipe. So I would choose the cylindrical one. Here, the idea is to get a maximum flow of materials in a pipe, you should shape the material to have same cross-section as the pipe itself. Now, let's take this into communication engineering. Most of the communication channels are considered to have a Gaussian distribution, and the widely known channel capacity limit formulated by Claude Shannon considers a Gaussian channel as well. And with the same analogy as in the previous slide, he formulated that the maximum bitrate is achieved when the channel is fed by a source with a Gaussian distribution. Let's consider a 64-quant constellation with which we can transmit a maximum of 6 bits per symbol. This figure here shows the probabilistically shaped 64 quant. So here, symbols are assigned with different probabilities of Gaussian distribution. Unlike the uniformly distributed 64 quant, this constellation now resembles a Gaussian channel. Let's see actually how the Achievable Information Rate can be increased using PS. The black dotted line here shows the Shannon capacity limit in bits per symbol for various SNR per symbol values. In addition to that, I have plotted the capacity of 4, 16, 64, and 256 QAM in these dotted lines. You can see in this lower SNR regions, there is a gap from the capacity limit. For example, if we look at the capacity gap of 256 QAM to achieve 7 bits per symbol, it is 1.55 dB far from the Shannon capacity limit. Now, if you include a capacity using PS shown in dotted lines for 4, 16, 64, and 256 QAM, you can see that PS allows the information rate to achieve the Shannon capacity limit. If you look at the same information rate of 7 bits per symbol, it is only 0.72 dB gap, which is an improvement of almost 50% over the uniform distribution. How about in terms of saving energy? In conventional uniformly distributed QAM, we have equal probability of transmitting high energy symbols as low energy symbols. Therefore, the overall symbol energy is high. In PS, however, low energy symbols are transmitted more frequently than high energy symbols. This probability depends on the choice of entropy in shaping the symbols. This figure graphically illustrates probabilistic shaped 64 QAM for 4 different entropy values: 5.88, 5.7, 5.4, and 5.1 bits. It can be seen that as entropy decreased, the higher the probability is for symbols in the most inside circle of the constellation to be chosen, and hence the more frequently those symbols are used. In this figure here, I have plotted the average symbol energy gain in percentage from PS over uniformly distributed QAM in terms of different choices of entropy for modulation orders of 16, 64, and 256. For 64 QAM, for instance, it is possible to have an average symbol energy gain from 22%, which is using 5.88 bits, to almost 60% at 5.10 bits. Now, various forms of multi-carrier modulation techniques, such as OFDM with combination of high-order QAM, have been applied to achieve higher spectral efficiency. In this workshop paper, we implemented a DC-biased optical OFDM system. And in our simulation, we start by generating random symbols both uniformly distributed and probabilistic shaped symbols. And these symbols are mapped in parallel to QAM constellation points. We consider 16, 64, and 256 QAM. To generate real value signals in time domain, Hermitian symmetry is applied to the frame prior to inverse fast Fourier transform operation. The symmetry signal is specified by padding 0 to the QAM signal with its complex conjugate in reverse order. After the operation of IFFT, the time domain sample is then converted into serial cyclic prefixes added, and then to ensure unipolar time domain signal required for intensity modulation of light emitting diode, a DC bias is added to the continuous time domain signal. The real unipolar time domain signal X of t is then used to drive the LED. We model the LED as first order low pass filter with a cutoff frequency of 10 MHz. At the receiver, the reverse operation to that of the transmitter side is implemented, and symbol error ratio of the system is evaluated by comparing the transmitted symbols with the received symbols under various SNR of the AWGN channel. Let's discuss the results of the simulation now. You will see here the symbol error performance of 16, 64, and 256 QAM for over a range of different SNR per symbol values. For all plots, black dotted points will show the theoretical values of symbol error performance, and the red lines will represent the uniformly distributed symbol error performance values. And the blue ones show the performance of PES. As it can be seen from these plots, the probabilistic shaped QAM outperforms the uniformly distributed QAM in these noise limited channel conditions. For example, if we consider a symbol error ratio of 10 to the power of -3, the SNR improvement is 2.1 dB for 16 QAM, 2.6 dB for 64 QAM, and 3 dB for 256 QAM. We have also shown that the performance gain increases at lower entropy values. And for example, for 256 QAM, if the entropy is decreased from 7.84 to 6.8, the SNR gain over uniform QAM increases to 5.5 dB at the same reference of 10 to the power of -3 symbol error ratio. To conclude my talk, I have presented to you a DC-biased optical OFDM based VLC system with uniformly distributed and probabilistic shaping applied on a symbol by symbol basis. I have also shown PS saving significant amount of transmission energy. The error performance results of uniformly distributed and probabilistic shaped signals is also discussed. And the probabilistic shaped QAM outperforms the uniformly distributed QAM in the noise limited channel conditions I discussed. With this, I will end my talk. Thank you for your attention.